Okay, so the plan for today is to discuss section 2.8. We saw 2.7, which introduced the idea, the formal definition, really, not the idea, but the formal definition of the derivative. Um, and in 2.8, we're going to look at the derivative kind of in a slightly different way. It's going to feel maybe pretty similar to 2.7. And that's really kind of the point of 2.8 is we're just taking a different perspective on that same material. And then I think it's good at some point in your mathematical career to see kind of explicitly a bit of a primer on the logic that we use, the propositional logic that we use. We're always talking about theorems and A implies B, and or maybe it's A if and only if B, and it's sometimes I feel like through your mathematical career, you're just expected to kind of pick these things up and get used to working with them. But I think it's good to actually lay out a foundation and know, if I see a theorem that says A implies B, what can I say from that theorem? Can I say anything else kind of immediately on the basis of A implies B, or maybe there are things that I instinctively want to say on the basis of that theorem that I really ought not say. That might be fallacies. So we're going to do a quick primer on propositional logic, and that should wrap us up for today. And then we'll start chapter 3 next time. The quote of the day today is by Horace, a Roman lyric poet. His book Satires, translated obviously from Latin. There is a mean in all things, too far to the right or left of which good cannot be found. So, in honor of in stats, we're covering means and measures of center and things. So I picked this one, but also in our discussion on logic, kind of interestingly, the word that he uses for mean is modus, M-O-D-U-S, and we have modes of argument and so on in logic. So kind of ties in a little bit today, and some of the argument, the modes of argument have Latin names. So yeah, so the plan for today is to start with 2.8, builds right off of 2.7. So the math should look pretty familiar here. So 2.8, the derivative is a function. Now, be a little bit careful. Some of you may have seen some calculus before, so you might have seen 2.7 and immediately made this leap in your head. And if you did, that's perfectly okay. But remember in 2.7, let me just actually jump back there really quick. In 2.7, we were looking at the definition of the derivative. We said we have a certain point and a function f, and we found the derivative at a point. So we were thinking of the derivative as a number, or maybe we were looking at a specific tangent line and looking for its slope, finding a number. Now we did actually, cheat the system a little bit. We found f prime of 3 was 6. But then we actually looked, we said, well, what about f prime of a? So we actually cheated the system a little bit here. We said, let me find the derivative of a number, but I'll leave it as an arbitrary number. And it's not too big a leap to say that, well, if I can take an arbitrary number that is the input, or at least an arbitrary number in the domain of the derivative that's an input, and that yields an output, which I call the derivative of the function at that input, that sounds an awful lot like a function, right? It sounds an awful lot like a function where I'm given an input, I do something to it, and it yields an output, and I can do this for a bunch of different inputs. And indeed, that's the leap that we're making today. So we say that the derivative, the instantaneous rate of change of a function f of x, is denoted f prime of x, and it's defined this way. F prime of x equals the limit as h goes to 0, f of x plus h minus f of x over h, provided the limit exists and is finite. What's the logical leap here? Here we're thinking of taking a function and transforming it to another function, right? It's the difference between it's the difference between saying, we have a function sine x and I want to maybe do something with it. Maybe I want to solve when is sine x equal 1/2 or something, versus taking sine x and transforming it, let's say turning it into sine of x all squared, something like that. I'm transforming one function into another function. I'm kind of establishing a process where I can take a function as an input into that process. So I have this process differentiation. And instead of thinking of taking like a function and a number in and getting a number out, I'm thinking of this process as taking a function in and it returning another function, which I call f prime. So again, it's maybe a little bit more of a philosophical leap in some sense, but this actually opens up some important doors to us. So it is important for us to take this philosophical leap. A couple of notes. First, there are a lot of notations for the derivative. Maybe too many, but I think that the ones that I'll introduce anyway all do serve a purpose, at least, let's say, an important purpose within the first 2 years of math, within the first 2 years of, say, math you would take for an engineering degree, the calc sequence, linear algebra, differential equations. You should see all of these at some point through those, say, 5 or so courses, um, and they should take on an important role at some point. And we can interpret this derivative, this function, the same way that we interpreted the derivative in 2.7. If I plug in a specific number for it, if I consider my function f prime of x and I put in x equals 2, I get f prime of 2. Well, that's just the same f prime of 2 that I got in 2.7. It's the same idea. It's, for instance, the slope of the line tangent to the graph at 2 comma f of 2. So some additional notation for the derivative. Here we take y equals f of x, and we have the good old f prime of x. We also have this, what's sometimes called like differential notation, this dy dx. They also call these like Newton versus Leibniz notation, and I can never remember which one's which. It might even be one of these that's the other one. But where does this dy dx come from? Well, let's just go with f prime of x, let's say, instead of f prime of a. Well, f prime of x is basically the rise over the run as, let's say, delta x goes to 0. But what is the rise? The rise is the change in the outputs. It's like delta y. And what is the run? The change in the inputs. We might call that delta x. So we're interested in investigating delta y over delta x as delta x goes to 0. Now we usually call it delta y and delta x when it's like when delta x is a number like 0.1 or 0.01 or something. But if we think of allowing delta x to approach 0, we kind of say that in that limit, it acts as an infinitesimal. It acts as something like a number that is positive but smaller than every real number, kind of in some loose sense. There are ways to formalize these ideas. But this is kind of the idea. We call it dy dx. And we'll investigate this idea, what does dy mean? What does dx mean? We'll see this in the linear approximations and differentials section later on in the course. So we'll investigate these details a lot more. But that's where this notation comes from. It's just kind of saying what is the infinitesimal rise, so to speak, when we have an infinitesimal run, when we have an infinitesimal teeny tiny change in the x variable. So this kind of to me has kind of a geometric connotation to it. So I mean, these all technically mean the same thing, but if I write dy dx, I'm usually kind of thinking geometrically. Not all the time. Sometimes there are other reasons to write it this way. I'm either thinking geometrically or I'm thinking more along the lines of like ratios of rise to run. F prime of x to me feels more functional. It feels more like I'm thinking of f prime of x like a function. And it's probably the most standard way to write the derivative. I could also think in terms of this kind of operator notation, where I'm thinking that this idea of differentiation here is an operation that is applied to a function that yields another function. For instance, the operation of squaring something, I could apply that to the sine x function and I get sine x all squared out. That's a different function. It was changed by that operation of squaring something. But I could put different things through that operation. I could put, square root of x through that squaring operation and I get something like x out the other side. So, um, this operation isn't necessarily inherently tied to, say, the sine function or the square root function. This operation of differentiation isn't inherently tied to a specific function f. I can take this operation, which I might choose to call d by dx, and apply it to a function of my choosing. Maybe in one problem, I want to kind of plug in f of x equals sine x and figure out what its derivative is. And in a different function, a different example, I want to plug in the function x squared, apply d by dx, apply that operation to it, and figure out what its derivative is. So this kind of makes me think of the focus in my mind as what function am I plugging in, and then applying this operation to. And that's basically the same thing over here, this big D f of x. Similarly, what function am I plugging in and applying the differential operator to? So we're kind of calling this differential operator either big D or d by dx. And again, these both have their place. They both have, you know, kind of areas where they're beneficial. Of the two, I'll almost always prefer this one. But in fact, when you get into, say, differential equations, you can actually do algebra with the differential operator. That's one way to solve systems of differential equations. And there, it's much nicer to write it this way, because then instead of trying to move around a whole d by dx thing as an algebraic component, I can just look at this letter big D. I know that it's a differential operator, but I can kind of treat it algebraically and move it around as if it was just, say, a variable. With some caveats and restrictions, of course, that's beyond the scope of this course, um, but that is maybe one of the nicest places to use the big D operator notation. Now, importantly, these are all representing functions. If I wanted to evaluate the function in whatever notation it is at a point, say x equals a, this is how I'd write it. So if I have the function f prime of x, it's equal to some, maybe x squared minus sine x or whatever. If I wanted to plug in a number a into that, I would denote that f prime of a the same way that I would any other function, right? F of x, if I want to evaluate that at x equals a, I just write f of a. I could write f prime of x vertical bar x equals a if I really wanted to be, explicit about things. If I wanted to use my kind of more geometric feeling dy dx and try to evaluate that at x equals a, I would probably represent it something like this. Maybe put the dy dx in closed brackets with a subscript x equals a. Or if I wanted to evaluate d by dx of f of x, I would write it this way: d by dx f of x at x equals a. I think most of these are straightforward, but I want to be really careful about one of them, particularly this last one. What I do not want to write I do not want to write something like this. Having like a heck of a time getting my trackpad to cooperate nicely with my brain today. I don't know if it's the trackpad or if it's my brain. I'm not sure. But I don't want to write something like this because remember what this notation means. Up here, what it kind of means is I have an operator that takes as input a function. So really what I'm saying here is, well, f of a is just the number. I mean, the only way I can really interpret a number as a function, if I just said the function is 2, is that it's the constant function. So here I'm like differentiating a constant function, but that's probably not what I mean, right? What I mean is differentiate this function, which maybe is like sine x or something like that, get that result, that resulting function, the derivative, and then evaluate that at x equals a. I want to make sure that I am careful that those are two separate operations. I get the derivative, I take the derivative, I get the function, which is the derivative first. Now I've got that function. After that, I want to plug in whatever input I'm interested in. I can't do it in the opposite order. If I do, then that's going to mess things up because when I evaluate the original function and then try to take the derivative, I'm kind of trying to do something like take the derivative of a constant function or even do something that just really doesn't make sense at all. If I'm trying to take the derivative of just a number, that doesn't make a whole lot of sense. So on one hand, it's a little bit pedantic to be this careful about things, but that mistake is an easy one to make, to do your differentiating and your evaluating in the wrong order and either end up really confused or end up just getting, the wrong answer. If you get 0 for all your derivatives, that's probably an indication that something went wrong. Okay, so what's an idea that we can introduce now? We've made this conceptual shift of thinking of the derivative as a function. So I have this black box differentiation, takes as input some function and gives as output a transformation of that function, which we call the derivative. So I start with a function. I input it into this black box differentiation, and I get out another function. There's nothing keeping me from doing this again, right? Because I have a function here, and it can serve as the input into the differential operator, d by dx, again, and I can get an output that's going to be some other function. And I could even do it again, right? I mean, presumably, at least as long as these limits keep existing and so on. So I could chain together this differentiation process and take the derivative of a function to get its derivative, or what we might now call the first derivative, differentiate the first derivative to get the derivative of that, which we might call, say, the second derivative, differentiate again to get the third derivative, and we could keep going on as far as we wanted and until either we get bored or the function kind of just ends up 0 and 0 from then on out, or maybe at some point the limits stop existing and then maybe after so many derivatives the fifth derivative doesn't exist or something like that. But we could keep chaining these together to get higher order derivatives. So some notation here. Again, just recall the notation from the first derivative, f prime of x, dy dx, d by dx of f of x, the kind of more operator notation, or df of x, again, another perspective on the operator notation. What would I, for instance, call this function that I get by differentiating the first derivative? What would I call the second derivative? Well, I have a few different options. I have kind of a higher order notation that's related to each of the four notations I've shown above. One of them is just to add another apostrophe, another tick mark. So f prime prime of x, which just about everybody would call either f double prime of x, or they would just say the second derivative of f, something like that. But if you wanted to verbalize this notation, you'd probably say something like f double prime of x. This looks a little funky. Let's come back to that. Let's focus on the differential operator notation. If I think up here, I have this operator d by dx that I'm applying to a function f of x. For my first derivative, I've applied it once. For my second derivative, I've applied it twice. I want to take a little tangent here, just a little side note. If I have a function like, let's say, f of x equals sine x, what do I mean by f3 of x? This can get a little bit confusing in trig, but most of the time what I mean by this is I mean f of x. I mean apply f, the function, 3 times. In other words, most of the time this would be like sine of sine of x. So when I see an exponent next to a function, that usually means apply that function 3 times in succession. And that's the structure that we're using up here. There is a little nuance, unfortunately, in trig, where if I have, say, something like, sine squared of x, that can also mean sine x times sine x. And it does kind of grind my gears a little bit that we use the same notation for 2 different things, and it's quite context dependent. But I would say unless the context is clearly here, we should probably default to successive applications of the function. So if I think of this notation, d squared by dx squared f of x, this is kind of like saying apply d by dx to f of x. I did that once. If I want the second derivative, I should do it again. I should take that as the input and apply d by dx to that. Or this is basically like applying d by dx squared to f of x. If I write it like this, there's just a whole lot of grouping symbols and parentheses. It's just kind of messy. So kind of by convention, we like distribute the squared, although that's not really what we're doing here. We're just saying that this is another notation that means the same thing as this, obviously kind of heavily, that notation is heavily influenced by the way that exponents distribute into division. But this is, this thing by itself would just be considered a notation. It's just a set of symbols. It's a set of pixels that just means a certain thing. It means apply the derivative 2 times. And the same thing goes here. We're just applying the differential operator 2 times. So we just write that capital D with a superscript 2 to signify the derivative of f of x. And now I think feeding back, that brings some clarity to this one. It looks like a typo at first. You're like, didn't you mean dy squared over dx squared? But dy squared over dx squared would kind of feel like the square of the rise over the square of the run, but that's not what we're doing here. We're getting something like rise over run, finishing that, and then we're taking that thing as the function that we now want to find another rise over run for that function. So, I mean, it might sound a little bit similar, but if you kind of write out the details, it's not the same thing. But I think this notation clarifies why we have this notation over here. We're applying this kind of d by dx twice to y equals f of x. So in the numerator, so to speak, I mean, again, technically this is just a notation, but in the thing that looks like the numerator, the squared only gets put on the d, and the denominator gets the whole dx. Higher orders for these three work basically the same way. The 2 just turns to a 3, a 4, a 5, to n, whatever number n is. For the primes, we can go up to f triple prime with 3 apostrophes. That's not too bad. If we start adding more than 3 apostrophes, it's really hard to tell the difference between like the 7th derivative or the 8th derivative if there's just a whole bunch of tick marks. So often we do one of two things. Well, maybe one of three things. We either switch to one of these notations that's a little clearer. That might be one approach. We might switch to Roman numerals in the exponent. So this is, it's kind of like, these tick marks, the prime, the double prime, are a little bit like prime, double prime, triple prime, like, 1, 2, and 3 in Roman numerals. And then we might switch to like Roman numeral 4, IV, or Roman numeral 5, V, or 6, VI, something like that in the exponent. So that's a fairly common way to go about it. I think as people are less familiar with Roman numerals these days, this might be a less popular choice. Also, as typesetting has gotten better, we have other options too. Another way to approach this is to use that same kind of functional notation, is to write our derivative as a superscript like this. And I wouldn't say, like, if I was to verbalize this, I wouldn't say something like f to the n of x or even like f to the fourth of x. That's not really, I would just say the fourth derivative of f or the nth derivative of f at this point. There's not really, as far as I know, a prime, f prime, f double prime, f triple prime. Those are kind of standard. But once you get to the fourth or higher derivative, I think you just start calling it, the fourth derivative, the fifth derivative, whatever. Now there's a little notational detail here as well. I kind of said down here that if we have, say, f superscript 3 of x, we take that to mean apply f 3 times to x. But what if I have f superscript 3 where the 3 is in parentheses? This also irks me a little bit because, usually when we're using parentheses, we could essentially get rid of them and it doesn't make all that much difference. But in this case, this is kind of a reserved notation. For instance, here, the third derivative. When you see that superscript on f in parentheses, and of course, this is going to be supported by context as well, that notation means the derivative. So we have quite a bit of notation here to get us off the ground. Kind of the good news is, we pretty rarely deal with any derivatives above the first or second. If we're dealing with higher derivatives, it's usually either because the extent of the problem is like compute the fourth derivative of this function, and that's just what the problem is about. Or maybe we're in some niche area like roller coaster design where we really care about not just position, velocity, acceleration, like all the kind of Newton's laws kind of stuff that we typically care about for things like forces, but also maybe like a jerk, what's the rate of change of acceleration? That can be something that creates stress on the human body and we want to understand, but those kind of things are, again, not super common. So we're probably not going to see very much above the second derivative very often at all. So that's a big plus, right? If you're familiar with these two lines of notation, you've got like 98% of the notation that you'll actually need for this course, and probably for most of Calc 2, Taylor's theorem at the end, not really, you'll need a little more for that, and for a good bit of Calc 3 as well. We're very interested in the first derivative, we're quite interested in the second derivative, third and higher. we more think of those as kind of corrections that we use whenever the first and second derivatives don't quite cut it. So there is information there, but it's maybe of less importance a lot of the time. But it is good to have kind of seen these a couple of times. And definitely in the first and second derivatives, be really careful with your notation. This notation is the way it is for a reason. It's meant to signify something specific. All right, questions so far?
Yeah, I have a question.
Yeah, sure.
I'm a little slow here, so I'm trying to touch base. So the function yields like a tangent line, right? Okay, I guess what I'm asking is, are we taking the derivative of the tangent line then, right after, like over and over?
Good question. So yeah, so what are we actually doing here? So if f prime is the slope of the tangent line, let's maybe come up here where I have a little bit of space. So the short answer, the cop-out answer to your question is we'll talk more about the geometry of this in chapter 4. But I do want to try to address your question here briefly. So we have some function like this, right? And this is f. If I pick a point of interest, say A, and I have f prime at A, so I have a tangent line here. Now, importantly, f double prime of A is not like taking f prime at A, or it's not like taking this tangent line and taking its derivative, because this tangent line is always a straight line, no matter what the original function was. Whether my original function was really simple or really complicated, the tangent line is always going to be a straight line, which means that in a sense, it's a fairly simple function, and within a couple derivatives, we don't have any more interesting information. So what are we really doing here? Well, we have to really shift our perspective and say, okay, well, really what f prime of x is, so that we can take a second derivative, is it's really saying for a bunch of different a's, I could get a bunch of different tangent lines. This might have, slope that's a little negative. This might have slope about 0. This might have slope that's a little positive. So what I can do now is I'd really like to write this graph below that one. Let me try to move this over. There, I think that'll be a little better. What I can do now is I can draw another graph. This graph I want to represent the function f prime. So I still have my x-axis. But I see that, like here, oops, I need a little bit more room in the bottom. I see that like here, for instance, it looks like the tangent line will be pretty much horizontal. So f prime will be, about 0 there. Over here, it looks like the tangent line is sloped a little bit up. So f prime will be maybe a little positive over here. Sloped a little steeper up further to the right, so maybe a little more positive over here. Or as I go to the left of this kind of 0 point here, as I go to the left, it seems like we're sloped a little bit negative. Seems like we're sloped a little more negative, a little more negative. So maybe I get an f prime function. I don't know, maybe it looks a little bit like this or something. So no, this is f prime of x. Now I can do the same thing. I can investigate, say for this A, I can investigate for this curve, what is its tangent line? So this, I'm kind of finding like the tangent line to the function that represents the slopes of bunches of tangent lines near the point of interest. This would be f double prime of a for this a. And I could do the same thing if I wanted. I could imagine, you know, the slope of f prime of x being a little bit positive here, being pretty positive there, being a little positive, being a little more positive, being very positive. And I could come down here and I could imagine another graph of f double prime of x, where what did I say it was? It was like a little positive here, a little more positive, a little more, a little more. And then as I go to the left, it's also a little more positive, a little more positive. So maybe f double prime looks a little bit like this. So if this was like a quartic function, this was like some kind of x to the fourth structure. I mean, of course, maybe shifted over and up a little bit, but this might be like a cubic function. This might be like a quadratic function. Um, and we will see, in fact, in chapter 3 that applying this differential operator to power functions knocks the power down by 1. But yeah, that's a very good question. And so it is important that when we're in section 2.7, we can just kind of stick to this kind of idea and thinking of the derivative as a number, no problem at all, or the tangent line as just being the tangent line at that point, period, end of story. But if we want to think of the derivative as a function, we have to imagine that we could put in a whole bunch of different inputs and get slopes of tangent lines as outputs for all those different inputs. That's what this graph represents. For each input, this is yielding an output that's the slope of the tangent line to f, to this original function up here at each of those inputs. This down here is yielding something else. It's yielding like the slope of the tangent line to the slopes of the tangent lines. And it's maybe a little bit unclear what that yields. What that actually yields is the curvature. It's something related to kind of this is curving up. Since this is like curving up everywhere, this is positive everywhere. So that's what it ends up yielding. But again, that's pretty difficult to see, especially number one, we just introduced the concept, so we're not used to working with it. And number two, we have quite a bit more calculus and intuition and background to build up before we actually get to that point. But so hopefully that answered your question a little bit. If you kind of got lost in the weeds there, no problem. This is material from a couple chapters from now. But this that's really why we are leaning heavily on re-envisioning the derivative as a function before we talk about higher order derivatives. But yeah, great question. Any other questions? Any other thoughts?
I wanted to note something about the higher order derivatives. When I was working with autonomous vehicles, we did a project to see like how many orders of derivatives we needed to account for to get accurate results. We went up to like 6 derivative of motion and found it was completely useless and waste of processing power. But the third derivatives are very important for robotics, keeping the delivery stuff that your payload safe and secure, keeping the humans secure that you're delivering wherever. For aerospace,
Mhm.
and computer science, that third derivative does come in pretty important.
Yeah, so so one of the big results in Calc 2 is called Taylor's theorem. And so this is a bit of an aside. So again, if you don't follow this, don't like feel bad or anything, but you can look it up in the book but basically the idea is that I can take a function and we'll see this first idea. This will be actually one of the main ideas in this course. One of the maybe 3, 4, 5 most important ideas in this course is, well, we can approximate a function by a linear function. We can actually not just say that this tangent line is somehow like some instantaneous rate of change, but I can actually say that the tangent line to a smooth function is actually a good approximation to that function over some range around the point of tangency. So I have something like, some constant plus, and what ends up being like f prime at a, f at a plus f prime at a times x minus a. This is what it ends up being. And if you work out, what would the tangent line formula be? This is what the tangent line would be. And we call this a linear approximation or a first order approximation. Now, for functions that aren't too curvy, that don't have too sharp of a curve, and so long as the inputs that I'm interested in being able to input and get output from, so long as those aren't too far from this point of tangency, if I'm staying relatively local, like my limit wants to keep me close, right? If my function is not too curvy and if I'm not going too far out, I get a pretty good approximation. My straight line, my tangent line looks pretty much like my function, and my output from this linear function is pretty close to the output from the other function, the original function. This is really nice if my original function is super complicated or super expensive to compute. If one computation of it requires, 200 multiplications, or even worse, 200 function evaluations, where here I have like one multiplication. This could be much more cost effective to compute. The downside is if my function is super curvy, the region where I stay close to the function from a straight line is much smaller. Or if my function does all kind of crazy stuff, my tangent line is maybe a decent approximation here, but terrible over there. It doesn't capture any of the interesting nonlinearities, essentially by design. So we could start adding in terms related to the second derivative or the third derivative. The benefit that we get is we start capturing some of this nonlinearity for complicated functions. And even for simpler functions, we tend to stay closer to the function for longer before we deviate. So we can expand our inputs where we can get good outputs much wider, and we capture some of the nonlinear behavior. The downside is the whole point of doing this is to replace a complicated function with a simpler function. I've just made my simpler function more complicated. So this is very much an engineering question, right? As engineers face trade-offs that mathematicians don't face. Mathematicians can just say, oh, we'll just use 1,000 terms and you'll be really accurate. But the engineer says, wait, but I need the thing to compute before like next century. So the engineer might say, okay, well, what's the trade-off between increasing complexity? It's more challenging to program, more challenging to debug, more costly because every one of these is another function evaluation or another multiplication or whatever. So what's the cost versus what's the benefit? The additional accuracy I get. And I think it was Dennis that was saying this, that it kind of sounds like for the particular application they had in mind, for that particular scenario, that particular function, that location, a lot of times you don't know what the underlying function is, so you have to estimate it. That's a whole other issue. So the accuracy increase that they were getting versus the cost they had to put in wasn't worth it after the third derivative. Maybe in some scenarios it's not worth it after the first. Maybe other scenarios you have to go to the seventh. It's just very situation dependent, I would say. But, kind of as a general rule, the higher the derivative, these terms start looking like terms with factorials on the bottom, and factorials grow very quickly. So if you're up to like the sixth derivative, you have a 6 factorial on the bottom. What is that? Is that 720? So you're like dividing the impact by 720. I mean, coupled with the fact that like how much information is there inherently in the seventh derivative anyway, maybe it's okay to cut it there.
So
So
it really just depends on how precise you need it to be.
Yeah, exactly. So I mean, it's very situation dependent, and you know, I'm sure they took a look at like what's the extra computational time required, what's the extra programming complexity required versus, and sometimes it also is very difficult to compute these derivatives. If you have a function that you're estimating based on data, getting higher derivatives can be quite challenging. Again, that's a whole other topic for a different course, but yeah, that so this idea of higher order derivatives definitely comes up very importantly in engineering and physics and all of that. Engineers and physicists love to get rid of these nasty functions by just making them linear functions or even quadratics or whatever. So um, yeah, definitely an important tool in the toolbox. Okay, so pretty straightforward definition. F is differentiable at A means that f prime of A exists and is finite. And saying f is differentiable in an interval I means f is differentiable at A for each A and I. And just saying f is differentiable, uh, typically that would be interpreted as f is differentiable on its natural domain, maybe plus or minus at the endpoints. So, I mean, ideally you'd be a little more specific than that, but if we just say, oh, it's a differentiable function, just speaking a little more casually, that means on its whole domain, maybe not at the endpoints. Okay, so let's find f prime of x when f of x is 1 over root x, for x is bigger than 0. And again, the mathematical details are going to look pretty similar here. We do tend to lean towards the h goes to 0 limit definition in this context. I guess we could like let t go to x or something like that in the other definition, but that's just a little funky to look at. Okay, so just plugging everything into the definition, this is what we get. And we could go a couple different routes here. Probably a good first step is to just multiply everything by square root of x times square root of x plus h. So if I multiply that on the bottom, I get this. And on the top, I get that. Okay, now I have a situation where if I were to just kind of, as I'm tempted to do sometimes, plug in h equals 0, I get a 0 on the bottom. I get root x minus root x on the top, a 0 on the top. I'm looking to do something to extract a factor of h out of the top that I can divide out with the h on the bottom, and then hopefully everything will proceed more smoothly. And we've seen this trick a couple of times. We multiply by the conjugate. So we multiply top and bottom by root x plus h. So multiply it on the bottom. The bottom doesn't look too great now, but it's nothing inherently problematic, just a little messy. And on the top, when I multiply by root x plus h, my first give me x, my outers and my inners cancel, and my last give me minus x plus h, being careful with that parentheses there. The minus hits the h as well. And need a little more room. X minus x, that goes away. I get a minus h over h, or a minus 1 over root x plus h. root x plus h. Okay. And now I look at this and I say, okay, if I plug in h now, I actually don't have a problem. So if I think through my limit laws, the limit of the quotients, the quotient of the limits, as long as that denominator doesn't limit to 0, I'm good. And the limit of the products, the product of the limits, limits break up sums, limits go inside of powers, all of that's looking good. So if I just plug in h equals 0, I get -1 over root x from here times root x from here. And be careful, root x plus root x is 2 root x. From there, take note that x is strictly positive. So we have not introduced the division by 0. And we get square root of x cubed, that's -1/2 x to the -3/2. Maybe writing it like that might be the nicest way to write it, but of course there's a dozen different ways you could, maybe not quite a dozen, but many different ways you could write this that are quite reasonable. Any questions on that one? If we put a in here instead of x and went back to 2.7, we'd have done the work exactly the same way. Or if we put a 3 in here instead of x, we'd have gotten down here and gotten -1/2 times 3 to the -3/2. We're just carrying that variable x through, and the rest of the steps really work the same. Okay, so let's take a look at this example. Where is f of x equals absolute x minus 1 differentiable? We know that this function is defined on the whole real line as a differentiable on the whole real line. Well, let's consider a couple of regimes. We know that f of x is x minus 1. Well, it's x minus 1 when x minus 1 is greater or equal to 0, or when x is bigger or equal to 1. And it's negative of x minus 1, or 1 minus x, when x is less than 1. Let me rewrite that. So this is what this piecewise function is. So as an exercise, you can consider the case x less than 1. And we'll take a look at 2 other cases. So we'll call this case 1, x less than 1. We'll look at case 2, x strictly bigger than 1. As well as the third case, x equals 1. So x is strictly bigger than 1. And let's pick h to be small enough so that x plus or minus h is also strictly bigger than 1. So we're picking like h in absolute value to be less than like half the distance between x and 1, for instance. Something like that would be fine. So what would f prime of x be for this function under this case where x is bigger than 1 and we have a small h? Well, that's limit h goes to 0 of f of x plus h minus f of x over h. But remember, when x is bigger than 1, f of x is just x minus 1. And again, if h is small enough in magnitude so that x minus h or x plus h, whatever, so that all of that is bigger than 1, the only inputs I'm considering are inputs into f that are bigger than 1. I can do that because since x is strictly bigger than 1, I can find an open interval that includes x that does not contain 1. Then I'm plugging x plus h into f, but that input is always strictly bigger than 1. My function under consideration is just x minus 1. Plugging x plus h into there, I just get x plus h minus 1. And I see that the x, they go away. The minus ones, they go away. I get limit h goes to 0 of h over h. Well, just to be very clear, this is limit h goes to 0 of 1. Keep in mind, limit h goes to 0, h is never equal to 0. If h is 0.1, I get 0.1 over 0.1, which is 1. If h is 0.01, I get 0.01 over 0.01, which is 1. The limit is 1. So for x bigger than 0, we see it's 1, or sorry, for x bigger than 1. For x bigger than 1, we see its derivative is 1. This case will show us that the derivative is negative 1 for x less than 1, but what about x equals 1? So that's the interesting case, where we're at the break between the two pieces of the function. So case 3, x equals 1. So what do I want to do? I want to find f prime of x, limit h goes to 0. Well, when x equals 1, f of x plus h and so on, I mean, I really can come down here and just say, really what I'm interested in is just finding f prime of 1. So that's f of 1 plus h minus f of 1 over h. Or this is limit h goes to 0 of what? Well, what's f of 1 plus h? That's absolute value of 1 plus h minus 1. Then minus f of 1. But f of 1 I can just evaluate. It's 1 minus 1 is 0 from the definition of my function over h. 1 plus h minus 1 is just h, so I'm looking for limit h goes to 0 of absolute h over h. Now be careful, this doesn't just divide out to 1. So if I look at this, there's a couple ways I can look at this. I can maybe look at a graph or whatever, but if I look at this in terms of its two one-sided limits, limit h goes to 0 from below of absolute h over h. Well, if h is negative, absolute h is just negative h. And now, because the h is outside the absolute value, it is able to just be divided out. But this is limit of negative 1, which is just negative 1. And likewise, the right-hand limit, maybe not likewise, but similarly, the right-hand limit when h is positive, absolute h is just h. But that limit is plus 1. These are not equal. This limit does not exist. F prime of 1 does not exist. So where is f differentiable? On the whole real line, except at 1. Does this mesh with our intuition, with our geometric intuition? Yeah, sure, this is an absolute value function. This just shifted 1 to the right. This is just absolute x, but I replace x minus 1 for x. surely any tangent line over here is well defined. Surely any tangent line over here is well defined. But at this point, that's where we have that corner. There's lots of tangent lines with different slopes that could touch just at that one point at that corner, 1,0 there. So we got an answer and meshed with our geometric intuition, our understanding of how absolute value functions work and so on. So it looks good. Any questions on that? And again, as an exercise, you can do the case where x is less than 1 and show that the derivative ends up being -1, which again is what we'd expect from our picture. Okay, so we have a couple theorems here. Oh, give me a sec to get my OneNote sorted out here. There we go. There. All right, there we go. I think everything is sorted out now. Good. So we've got two theorems here to wrap up the material from section 2.8 and the kind of formal material from chapter 2. And then we have our primer of propositional logic. Might or might not have time to get to it today. We'll definitely have time to start it, but might or might not have time to finish it today. So the first theorem is, I've written it a little bit loose here intentionally, because we'll kind of maybe refine this throughout chapter 3. But first theorem, the derivative of an odd function is even, and the derivative of an even function is odd. So if I have a function with a symmetry, either odd or even, and I kind of put it through that derivative black box, presuming that the derivative exists and all that kind of good stuff, then the resulting function, its derivative, will have the opposite symmetry. Odd functions turn into even functions and vice versa. There's kind of an interesting, deep reason why this happens related to actually Taylor's theorem and so on. That's also the deep reason why they're called odd and even functions. Little hint, the Taylor series for odd functions only has odd power terms, and the Taylor series for even function only has even power terms. There's a little preview of the end of Calc 2. But and if we know the derivatives knock power functions down by 1 power, maybe we can kind of start to put some of it together. But we're not going to use any of that in this theorem. I just figured I'd throw that in because we did talk a little bit about some of that a little earlier to answer a couple of the questions. So we're going to prove that the derivative of an odd function is even, and we'll leave it as an exercise to show that the derivative of an even function is odd. So that might be a nice little exercise to do as you're rewriting your notes. It'll be a very similar proof. Okay. So what do I need to show? Let's say let f be odd. In other words, f of negative x equals negative f of x. At the beginning of a proof, it's never a bad idea to just remind ourselves what we need to show. I want to do some algebra, some using definitions, some algebraic manipulations, and so on, some argument to show that its derivative is even, to show that f prime of negative x equals f prime of x. That's just using the definition of, this is the definition of what it means to be an odd function. This is the definition of what it means for the derivative to be an even function. Okay, so where can I start with this? Well, maybe I'll start with taking one side of my need to show equality here, say f prime of x. I know quite a bit about this. I know the definition of the derivative, all this kind of stuff. And then I'll try to do some algebraic steps to work my way through and show that's equal to f prime of negative x. So maybe I'll do this, I don't know, let's say in green. So f prime of x, by definition, it's equal to limit h goes to 0, f of x plus h minus f of x over h. Now what can I say? Well, I can say that because f is odd, well, if I have what? Minus f of x here, I could turn that into a plus f of negative x. I know that I'm going to have to use the oddness of this function somewhere. So minus f of x by the oddness of the function turns into plus f of negative x. That's essentially what an odd function is. It means that you can take minuses from like inside the function and pull them out, or from outside the function and push them in. They kind of the minuses pass through the function in a little bit of a similar way to like for continuous functions, the limit passes through the function. It's kind of an analogous kind of idea. So that took care of this guy. That this over h, I suppose, is going to just stick around for a minute here. Now f of x plus h. I don't see any real, I don't see any negatives floating around there, but I noticed that my definition of odd function, I can rearrange it a little bit. So f of negative x equals negative f of x, or I can multiply both sides by -1. So for an odd function, I can, in a sense, put in a negative on the outside and on the inside, and they kind of inherently cancel out. So maybe I can make this negative f of, and let me be careful here. Well, first, let me be careful to not run my negative into my f and forget about it or something. But negative f of, I have to be careful because I don't want to just make this negative x plus h. This is really negative of the whole argument, right? The entire input into the function gets negated. So I need to make this negative x minus h. Easy mistake to make to miss that minus on the h. But it's really the whole argument, the whole input into the function that's getting all overall negated. Okay, so let's double check that. I turned my f of stuff into negative f of negative all that stuff. And my minus f of x turned into a plus f of negative x. So I just pushed that negative inside. Looks good so far. So I use the oddness of the function here. But now I've got a little bit of a situation. Everything is kind of jumbled about now, right? Now I do remember, you know, if I'm a little stuck here and I'm saying, what is my goal? What am I looking toward? I started here. I'm looking to get f prime of negative x. Let me actually just come off to the side here and say, what exactly is it that I'm looking to get? What is f prime of negative x? Well, that is limit h goes to 0. F prime of x would be f of x plus h, but f prime of negative x is f of negative x plus h. Note the plus there. I've just swapped x for negative x in my definition. Minus f of negative x over h. I noticed that this like minus f of negative x, I have a plus f of negative x. I need to switch that sign. So what could I do to switch that sign? Maybe if I multiply top and bottom by a negative, you'll switch colors here. Right, this f of negative x, there's not a whole lot going on there. There's not much I can do with this to make it look like negative f of negative x other than multiplying it by -1. So if I multiply top and bottom both by -1, well, first that cancels out the negative in front of here. And hey, that's looking a little better. F of negative x minus h versus f of negative x plus h, a little different, but they're getting closer. That multiplication by -1 got rid of the minus on the first term and added a minus on the second term. That minus f of minus x now looks pretty good. And I got to multiply it on the bottom as well, right? So the h turns into a negative h. And here I'm almost done. I have f of negative x minus h minus f of negative x over negative h, f of negative x plus h minus f of negative x over positive h. If only my h's were positive instead of negative. This introduces another nice thing that we can do in limits. We can change our variable that we're using for the limit. Let me, instead of using h, let me use k equals negative h. Now as h goes to 0, k goes to 0 as well, right? When h is a little bit positive, k is a little negative, or when h is a little bit negative, k is a little bit positive, it switches signs, but it still goes to 0. If we were dealing with a one-sided limit here, we'd have to be really careful, you know, if h was going to 0 from above, k would go to 0 from below, but h is just going to 0 overall, as is k. And negative h equals k. And one thing that I should realize about the limit is that the limiting variable, I called it k here, but it's just a dummy variable. When I end up computing my limit, when I end up computing, you know, limit as h goes to 0 of whatever, I don't have any h's left. When the limit goes away, so does the h. It's just a dummy variable that the limit uses. It doesn't much matter what we call it. It doesn't have any relation to x or my function or anything like that. So the fact that I chose to call it k now doesn't really matter. If it really bugs you that much, you can come back and you can, you know, oops, k equals h. And of course, as k goes to 0, h goes to 0. We could just basically rename k back to h if it really bugged you that much. But we see immediately that this is the definition of f prime of, and whatever we have here, as long as they match, is what we're inputting into the derivative, negative x. We see this is just the definition of the derivative for the function f of negative x. But wait, I showed that if f is odd, and of course, you know, implicitly assuming here if the derivative, if the limit exists, but if f is odd, then f prime of x equals f prime of negative x. But that was what we needed to show. F prime is even. And again, as an exercise, do the other one. Show that if f is even, then f prime is odd. The details will look very similar to this one. This is actually a really nice theorem to remember. It's kind of a nice check sometimes on your functions, especially if you recognize that symmetry. Number one, it makes a nice check on your functions. Number two, it can actually save a lot of time. If you see the symmetry in the original function and you can use it in the first or second derivative, there are some scenarios where that saves you a lot of time, and you can use kind of the work you did on one side of 0 and just flip it over to the other side of 0, for instance. Any questions on this one? Okay. Okay, and then a last theorem. The previous theorem was a nice theorem, but I would say this is, one of the more important theorems about derivatives for a couple reasons. One is, frankly, because people get it wrong so often. And that's where this primer on logic is going to come from. We're going to use this theorem as an example in there and talk about the ways that we could misinterpret such a theorem. And that will help us to make sure that we don't misinterpret this theorem, but also hopefully don't misinterpret other theorems. So theorem, if f is differentiable at a, if f prime of a exists and is finite, then f is continuous at a. So we're linking the ideas of differentiability and continuity here. So let's prove this one. So what does f differentiable at a mean? It means, and here we're going to use the limit x goes to a definition of the derivative, works a little bit nicer in this case. It means that this limit exists and is finite. Or in particular, that this equals, let's say, a limit L, a real number. So this limit equals L, a real number, not minus infinity or plus infinity. That's going to actually be pretty important. So what can I say then? What I would like to show is that this condition, limit of this difference quotient equals L, a real number, forces f to be continuous at a. It forces that limit x goes to a f of x equals f of a. That was our definition of f continuous at a, right? Let me actually write that out just as a reminder. Right. That's, of course, the reason that we're using the similar looking limit for the derivative, because it's just going to mesh with our definition of continuity a little nicer. So that's what it means for a function to be continuous. I kind of like gut feeling believe this to begin with, right? Those are kind of the, that's a nice place to be at in a theorem. Because I'm thinking, okay, if x goes to a, if the bottom goes to 0, if f of x didn't go to f of a, like, how does the bottom go to 0, the top not go to 0? That should blow up. But it doesn't blow up. So it seems like that top ought to go to 0. Like f of x ought to get closer and closer to f of a. Well, that's just saying limit x goes to a, f of x equals f of a. So gut feeling, that seems to kind of check out. So where does that kind of analysis come from? Well, it comes from looking at the fact that limit x goes to a of x minus a is 0. So my bottom is like going to 0. Now, what can I do here? I suppose maybe I could try to multiply by limit x goes to a of x minus a. Ideally, I'm thinking that, okay, my x minus a's will end up canceling. I'll be left with just limit of f of x minus f of a. And then I have like limit of the difference of the limits, and then limit x goes to a of f of a is just f of a. And I should be able to rearrange and get something that looks like this, and I should be able to get something that looks like that, and hopefully kind of make this work out. Now, the only real equation that I have to work with to be able to stick something onto the end of this and be able to do it to both sides is this equation up here. That's why I gave this limit a name. I named it L so that I could say equals L times and the same thing. Right? There's no problem doing that. I just took something and multiplied it on both sides. But in fact, I mean, on the right-hand side, I know what this limit is. Limit x goes to a of x minus a. I know that that's just 0. So why not just multiply by 0? And that's, of course, equal to 0. So it ought to be true that the product of these two limits equals 0. The first limit exists by assumption f is differentiable at a. The second limit exists by basic theorems. Pick your 2 or 3 basic theorems now that said that. So I have two limits that exist. Their product exists. I should be able to wrap them under a single limit. And when I do that, the x minus a is divide out. And then here again, I have the limit of the difference is the difference of the limits. So I could write this, but I know that limit x goes to f of a is just f of a. F of a is just a constant. Oops, went a little too far there. And of course, I can just move the f of a onto the other side, and I see that f is continuous at a. So if f is differentiable at a, if f prime of a exists, then f is continuous at a. Any questions on this? So we have here a pretty nice, pretty easy to understand theorem that's a very kind of clean theorem. If this one kind of fairly simple in a sense thing is true, at least simple to state thing is true, then this other simple to state thing is true. And that's, at the heart of it, that's what most of our mathematical statements or theorems look like. They either look like if one thing is true, then another thing is true, or they might look like these two things are equivalent. And so that's what we're going to use as kind of the starting point for our discussion on logic. So any questions on anything in chapter 2 before we kind of really shift gears here for a bit for the last little bit of this class and part of the next class. Okay. So our mathematical statements, our theorems, are usually one of two types. Kind of the A implies B type, or the A if and only if B type. This is like if proposition A, or if statement A is true, then statement B is true. If f is differentiable at A, then f is continuous at A. Over here, this is like A if and only if B. So like x plus 1 equals 3 if and only if x equals 2. Right. So this is true in either direction of implication. If x equals 2, then x plus 1 equals 3 for that value of x. And if x plus 1 equals 3, then x equals 2 for that same value of x. Sometimes we say A implies B over here as well. And over here we might say A is equivalent to B. Right, we often call equations with the same solution set equivalent equations, for instance. Note that A if and only if B really kind of means two things. It means A implies B and B implies A. Okay, so that's what most of our mathematical statements, most of our theorems look like. So let's consider some things that we might want to say on the basis of, say, a simple, type 1 theorem, A implies B. The type 2 theorems are just kind of two type 1 theorems together, right? All right. So let's consider the proposition itself. Consider the proposition A implies B. So here we have, let's say, some theorem that we proved. We say, okay, this is a statement of fact. If f is differentiable at A, then f is continuous at A, or differentiability at A implies continuity at A. This is a statement that we've established as fact, or at least have agreed upon as fact. We have a couple of names for things. We call A the antecedent, and we call B the consequent. So B is kind of the thing that follows is kind of the consequence of the first thing. And the first thing, like if you've ever heard of like antechamber or something, it's ante means like up front. So the antecedent and the consequent. One example I like to use for this, it's a bit of a silly example, but I like to think of like in a utopia, we have like dogs who all have four legs. There's no, three-legged dogs that lost a leg for some reason. So I like to think of animals and the number of legs they have. I think it's just very tangible and relatable and easy to understand rather than mathematical theorems. So for example, we might say A, it is a dog. So if I look at an animal and I see that it's a dog, maybe I have a theorem in my utopia that says if it's a dog, then it has four legs. That seems like a pretty reasonable theorem in a perfect world, right? So B, it has four legs in our utopia again. Nothing in the real world works with perfect implication. So we have to kind of imagine a little bit. So A implies B says if it is a dog, then it has four legs. And I think we'd agree with that in a perfect world. That's kind of, one of the like, I don't know, like platonic characteristics or something of a dog, that it has four legs. If it's a dog, it has four legs. That's our proposition itself. And we're going to kind of riff off of this proposition for these next couple of points. So we could make another variation of this proposition, A implies B. We can make a variation that we call the contrapositive. So consider the contrapositive. In logical symbols, we would write it this way. Not A implies not B. So this little like over and then down little thing is not, it's contradiction. Or simply not A implies not B. Oh, I'm claiming brain fog from getting over being sick on that one. I need to switch the order of those. Switch A and B. So not B implies not A. That's what I wanted to say. Not B implies not A. Or we could say if B is false, then A is false. Now, what's important to realize is this is a variation. It's a separate proposition from our original one. We established our original proposition. Maybe that was our theorem, differentiability A implies continuity at A. Maybe that was our dog theorem. If it's a dog, then it has four legs. We kind of agree on that. But here we've kind of switched some stuff up. We switched the order, we've negated some things. It's not really clear whether this is still true or not. So right now I have like a big, question mark as to the validity of this statement. This is another statement. It might be true. It might not be true. I'm not sure yet. Let me see what it says in terms of dogs and legs. So not B means it does not have four legs. So not B implies not A. What is this claiming? We still have to decide whether we agree with it or not. But what it's claiming is not B. It does not have four legs. Then not A. It is not a dog. This is our potential new theorem, our new statement that is based off of the old one, might or might not be true. Does this seem like something that we can conclude? Well, sure, if all dogs have four legs, if I look at an animal and it does not have four legs, it cannot be a dog in our perfect world again. So this is actually true. Does it seem like it's true just by happenstance, or is it actually fundamentally true? This is actually fundamentally true. If any time that A exists, if anytime statement A is true, then B must also be true. If I know that B is false, A cannot be true. One of our assumptions in propositional logic is that a thing cannot simultaneously be true and false. It has to either be true or false. It can't be both. If this statement was false, if not B implied A, so if I had not B, but I had A, but up here it says if I have A, I have to have B, I would have not B implies A, and then A implies B, so not B implies B. So B being false implies that it's true, and that doesn't work in propositional logic. Maybe if you study philosophy long enough, you can come up with crazy logical systems where they maybe admit things like that, but not here. So this has to be true, right? Not B implies not A. Okay, so from the dog standpoint, if it does not have four legs, then it's not a dog. Or the contrapositive has the same truth value as the original statement. Maybe I'll put that kind of in red. This has the same truth value as the original proposition. What does this mean for a mathematical theorem? If I have theorem A implies B, I get another theorem for free. I get not B implies not A for free. It's just the contrapositive. Or if I want to prove a theorem, I have a statement that I want to prove. Maybe it's kind of annoying to prove it this way, but if I switch it around to its contrapositive, maybe it's easier to prove it that way. And since the two are logically equivalent, proving the contrapositive proves the original theorem, right? So I could look at it either of those ways. So if the proposition is proven, the contrapositive is also true. The next two we're going to look at are the converse and the inverse, which we might be tempted to think are also true, but spoiler alert, they are not true in general. There can be cases where the converse happens to be true for this case, but it is as a general rule, you can't say the proposition is true, therefore its converse is true, or therefore its inverse is true. So these are what we call logical fallacies. If we were to say that the converse or inverse are true because the proposition is true. And that's where we'll pick up next time. Let me stop the recording.